All right, so in this lesson, we are going to look at using our algebra skills to find the domain of a square root function. We've looked at this a little bit in the context of once we found the inverse of a quadratic function, we then found the domain of that inverse, which was a square root function. These are going to be a little more complicated in some ways. All right, so the algebra we'll use will not always be simple basic algebra. All right, so we're going to build up to that though. So your domain of your square root function is have to make the radicand non-negative. So remember that means greater than or equal to 0 because you've got the square root of 0 is 0. You can have a radicand that is 0. And to make sure you get real number values for your range, your radicand has to be positive, so you don't get any I situations. So this is our basic procedure if we're dealing with a linear structure for our radicand. So you just set that radicand greater than or equal to 0, and then you use your basic undoing algebra, reverse order of operations, to solve for x. Do remember to keep in mind any relationships, those algebraic steps that change the inequality relationship. Do you guys remember? Well, remember when those are would be when you multiply or divide both sides by a negative. So if you multiply or divide both sides by a negative number, then you have to switch the inequality symbol. And you can also check yourself once you've done your domain by plugging in values that represent your inequality to make sure that you don't get any I situations, no square roots of negatives. All right, so let's take a look at this one. So we are going to find the domain. And once we know what our domain is, we are going to use both our set notation, which is our inequalities, and our interval notation that's equivalent to it. So here we've got our function. G of x equals 2 times at 5x, the square root of 5x minus 3 minus 2. So remember, here's the thing you got to remember, that when you're finding the domain of the square root function, the key thing is that we're choosing domain values so that the range will all be real numbers. And so we're looking at our radicand. That's our radicand, what we are taking the square root of. That has to be non-negative. So our 5x minus 3 has to be either greater than or equal to 0. So in a linear situation, remember, you're doing reverse order of operations. So you'd add 3 to both sides, and then you divide both sides by 3. Sorry, divide both sides by 5. And you get greater than or equal to 3/5. Nowhere did we have to multiply both sides or divide both sides by negative, so our inequality stayed the same the whole time. So your set notation, that's with your inequalities. The set of all x's such that x is greater than or equal to 3/5. And your interval notation would go from 3/5 to positive infinity and does include 3/5. So that means on the 3/5 side we have to use a bracket. It goes all the way to infinity, which we use a parenthesis on. And that would then be both forms of our domain. All right, in this one, so now we've got g of x equals the square root of -1/2 times the quantity of x plus 2. And the plus 1, notice, is outside of the radical, which means that this -1/2 times the x plus 2 in parentheses, that is our radicand. So our radicand in a square root function always has to be non-negative. So that means it has to be greater than or equal to 0. So we're looking at -1/2 times x plus 2 must be greater than or equal to 0. Now, when you solve this, there are a couple of different ways that you could go. You could distribute the negative 1/2, but I would not recommend it. It's unnecessary. We're going to undo the multiplication here that's outside of our parentheses first. So we're going to multiply both sides by the reciprocal, because undoing this would be dividing by negative 1/2. So that's procedure, remember, is to multiply by its reciprocal. So we're going to multiply both sides by negative 2. Negative 2 times negative 1/2 would be 1, because they're reciprocals of each other, and that gives us x plus 2. And 0 times anything is still 0. But here's where we have to realize we did multiply both sides by a negative number, therefore our inequality is no longer greater than or equal to, it is now less than or equal to. And then we continue the solving, so subtracting 2 from both sides now gives us x is less than or equal to negative 2. So we have our set notation. Would be the set of x's such that x is less than or equal to negative 2. And our interval notation. So now our interval notation, we have to realize less than the negative 2 would take us down to negative infinity. And intervals are always written least to greatest. So we have to start with our negative infinity, end with our negative 2. And because negative 2 is included, we have the equal to negative 2. We use a bracket on the negative 2 side. All right, so in many square root functions, our radicand is not a linear structure. It's quadratic or even something else sometimes. Here we're going to look at if we have a quadratic expression as our radicand. So you guys learned how to solve a quadratic inequality last year, but it's been a while. So we're going to go over that procedure again here. So you still, of course, conceptually, your radicand has to be non-negative, greater than or equal to 0. But in order to figure out where it's going to be non-negative with a quadratic, quadratics will have 2 real solutions when they have real solutions, or 1 real solution. And so we have to figure out where our values of x are equal to 0. And once we know, those are the the values of x that will make that 0. Once we know what those are, what make the radicand equal to 0, it creates intervals. And so we set up a number line using those values. And then we have to test each of the intervals that are created on that number line with those numbers to determine whether we're going to get positive or negative values in each of that. So the domain values are going to be where it creates the positive intervals. So the domain is going to be the values of x that create the positive interval values. So we'll see how that looks. All right. So here we got g of x equals the square root of x squared minus 12, then a plus 10. The radicand is our x squared minus 12. So that is the part that has to be non-negative. So it's only the x squared minus 12 that needs to be greater than or equal to 0. What we actually need, though, you cannot solve this like you do a linear. You can't add 12, take the square root of both sides, and have that be your domain. It actually doesn't work, okay, because of the inequality symbol. What we are going to do is we are going to figure out, so once we understand what needs to be non-negative, we're going to figure out the x values that make x squared minus 12 exactly equal to 0. We're going to solve this. And this we can use our basic undoing algebra on. So I would undo my subtraction first, giving me x squared equals 12. And then I would undo the exponent of 2, taking the square root of both sides. Now here we are using the full square root property, which means we need to understand x can be positive or negative. So we have the square root of x squared equals plus or minus the square root of 12. And so our square and square root undo each other. We get x equals. In this case also, we would be expected to simplify the square root of 12, which remember is the square root of 4 times the square root of 3. So we get positive or negative 2 times the square root of 3. All right, so now what we're going to do is we are going to construct a number line. And this represents basically our x-axis. And we're going to plot our square root of 12 and our negative square root of 12. So we know 0 is somewhere around in the middle. We've got our positive square root of 12, or 2 root 3, and our negative. You might recall that what these actually represent are the zeros of the quadratic function f of x equals x squared minus 12, which means that these are where the parabola that comes from x squared minus 12 intersects the x-axis. So there are a couple of different ways that we can approach this. We can do the algebra, and we want to pick a number, such as I like to use 0, which is in this middle section here, and I want to plug it into x squared minus 12. And I want to know, is it when I plug into 0 going to plug 0 into x squared minus 12, is that going to be a positive number or a negative number? And well, 0 would be 0 squared minus 12, which would be 0 minus 12, which would be negative 12. So I'm looking at, okay, I've got 0 squared minus 12, that would be negative 12. So this is a negative section in the middle. I can do the math over here. I need something that is smaller than negative square root of 12, which, like, for example, negative square root of 16. 16 is a perfect square, so that would be a negative 4. So I could use negative 4 over here. So I'm looking at, all right, what is negative 4 squared minus 12? Well, that's 16 minus 12, which is 4. That is positive. And over here, I could use something like positive square root of 16, which is 4. So that would be 4 squared minus 12, which would be 16 minus 12, which is 4, which is also positive. So the math here, these positive sections on my number line, these are my domain sections, including my positive and negative 2 root 3. Another way of looking at it, for those of you who are more spatially or graphically inclined, what this is telling us is f of x equals x squared minus 12 has an a value of 1. So this is a parabola that opens up and crosses the x-axis at positive and negative square root of 12, which means it's a parabola that looks like this. And the sections of the x-axis that create those positive y values are the domain of the expression. So they're the domain of this square root function, because this is where this quadratic is going to be greater than or equal to 0. So from this, that section is part of our domain, and this section of values is part of our domain. So when I go to write my solution, my set notation, so here we have 2 separate intervals. Those are each going to be their own inequality and their own interval. So we've got the set of all x's such that these would be x's that are less than or equal to negative 2 times the square root of 3. Or these would be x's that are to the right, so they're greater than or equal to positive 2 times the square root of 3. Interval notation. So this would go from negative infinity to negative 2 root 3. So we have from negative infinity to negative 2 root 3 with a bracket with the negative 2 root 3 because it's included, in union with the second interval, which starts at 2 root 3 and goes to positive infinity. So we have a bracket with our positive 2 root 3 going all the way to positive infinity for our interval notation. All right, so for this one, we have g of x equals the square root of 49 minus x squared and then our minus 1. So our radicand, the part that has to be non-negative, is 49 minus x squared. So we know that 49 minus x squared has to be greater than or equal to 0. Be careful here. One of the biggest mistakes I see here is with people who think that they can solve this like they do linear. It doesn't work that way, ever. So what I'm looking at is understanding my first step is to figure out where is 49 minus x squared equal to 0. Now here, personally, I would probably add x squared to both sides, giving me 49 equals x squared. Then I would use my square root property. So the square root of x squared is equal to the positive or negative value of the square root of 49. This time I've got this nice perfect square. And square root of 49 is 7. So I get positive and negative 7 as my values. These are the values of x that make our radicand 0. But they do also correspond to, on our number line, where the function f of x equals 49 minus x squared is equal to 0. And so they are the zeros of a parabola. So what I like to do is find the interval where 0 is, where the x value of 0 is. It's not always in the middle, so don't make assumptions there. Here it's in the middle, so I would figure out, okay, what happens if I plug in 0 to 49 minus x squared? So I'm looking at 49 minus 0 squared. That would be 49 minus 0, which is 49. So this section is positive. Now, you can go through and you can do the others. Like, for example, I can choose positive 8 over here. And then I've got 49 minus 8 squared. That would be 49 minus 64. And I don't really care what number it is. I just care that I understand it's negative. And you could do the same thing over here with like negative 8, which gives you 49 minus negative 8 squared, which is also 49 minus 64, which is also negative. So you can do all that math. You can also understand that with a quadratic like this, you are going to get an alternating pattern. So once you know one section, we knew this was positive. We knew that on either side of it, it has to be negative. Another way you can look at it is that this is also equivalent to the zeros of the function f of x equals negative x squared plus 49. And your a value is negative, which means that you do have a reflection across the x-axis. And so your parabola opens down. Now you still, whether you can do all this, you now have to be able to interpret this information. And you need to understand that wherever you're getting these positive values, wherever your parabola is above your x-axis, those are the x's that represent the domain of the square root function. That's our domain. So now, when I look at this to do my set notation, this is one interval, but it does have to be represented with what we call a compound inequality, because these are the numbers between and equal to negative 7 and positive 7. So our set notation, if you recall, looks like the set of all x's such that negative 7 is less than or equal to x, and x is also less than or equal to positive 7. And our interval notation, this would be one single interval. from -7 to +7, and both -7 and +7 are part of the interval, so we use brackets on both. So this is the interval from -7 to +7, like so. All right, so in this example, our radicand is still a quadratic, but it's a trinomial. So we're again looking to make sure that our radicand values are non-negative, which means that any x we use has to make x squared minus 5x plus 4 greater than or equal to 0. But again, we can't solve this directly with algebra. First thing we need to do is figure out what values will make this trinomial equal to 0. So it's like solving this little quadratic equation. And again, I would use factoring whenever possible. I can factor this into x minus 4 times x minus 1. Zero product property tells me either x minus 4 has to be 0 or x minus 1 has to be 0. So my x's would be +4 and +1. So these are technically the zeros of the function f of x equals x squared minus 5x plus 4. And so this number line is using that related concept. Be careful. Remember, this is a number line. So make sure your numbers are in the correct positions, least to greatest. The smaller number should be to the left. So 1 has to be here, 4 has to be there. When I go to test my number line here, again, don't assume 0 is not between 1 and 4. Where is 0? It's over here. So I'm going to figure out this section first this time. So I'm figuring out what is 0 squared minus 5 times 0 plus 4. And that's going to be 4, which is positive. So this section's positive, which means my middle must be negative, and then the far right must again be positive. So these guys are like the zeros of the function f of x equals x squared minus 5x plus 4, which has an a value that's positive, so there's no reflection. So that's what we're looking at graphically, is a parabola that opens up. So the domain of the square root has to be the x's that create these positive y values. So this is part of my domain. And these x's are part of my domain. So now I'm looking at, for my set notation, set of all x's such that, so these are to the left of 1, so that would be x's that are less than or equal to 1. Or, over here, these x's are to the right of 4, so they are greater than or equal to +4. And then the interval notation. So this has its own interval, less than, so that would be from -infinity to 1 with a bracket at the 1 because it's included, in union with from the 4 to +infinity for numbers greater than or equal to 4, like so. All right, so that is our final example and will be the end of the lesson. Have a good day.